This video will be talking about how to draw and use free body diagrams. So free body diagrams, or FBDs, are used in force calculations, and we will be using them throughout the course. It's a very simple way of being able to visualize what's going on. A couple things. We usually draw the object, no matter what it is, as a rectangle or a box, and the surface as a straight line. Forces are vectors, so we draw them as arrows showing the magnitude and the direction, and the mass of the object is usually just written inside the object with the units. And the direction of A is usually in the same direction as F net. So here's an example. A car with a mass of 1,800 kilograms is pushed across a frictionless surface with a force of 600 newtons. So I draw my box, I draw my surface, I draw the mass inside the box with the units. So an 1,800 kilogram car, don't have to draw a car, pushed across a surface. So I draw all my force vectors. I know that there's going to be the weight of my object pushing down on my surface, and the normal force of my surface preventing that object from sinking in. These arrows should be the same length. Then I have a force vector, and it doesn't matter which way I'm pushing it. I can push it to the right or push it to the left. I could even look like it's pulling the object. It doesn't really matter. But I only have one force pushing it in this direction. And so my net direction of motion is going to be this way. My F net is into the right, so my acceleration will be to the right. Second example, same car, but now I have friction. So I'm pushing the car with a mass of 1,800 kilograms with a force of 600 newtons, but another force, 200 newtons, pushes in the opposite direction. So again, I have my box, I have my surface, I have the mass written inside it, I have Fg and Fn with the same magnitude of arrow, same length, pointed in opposite directions. These are going to cancel one another out. The box is not moving up or down. But what is happening is that I have a force pointing in one direction that's 600 newtons, and a smaller force, and it's shown by the length of the arrow, that's moving in the opposite direction of 200 newtons. So these lengths of the arrows don't have to be perfectly proportional. Like this does not have to be 3 times exactly the length of this, but just so that your brain can realize, oh, the general direction, the force that's going to win out, so to speak, is going to be the 600 Newton force. My acceleration is going to be in the direction of that motion. I can also draw it this way. If it's easier for your brain to see which force wins out by stacking them on top of each other, by all means, do that. You don't have to say just because they're pushing, they have to be pointed toward the box. This one's pointing in one direction, this one's pointing in the opposite direction, and here I can clearly see, oh wow, this is much larger than this one. A is going to be going that way. Here's another one in the y direction. So I have a 50 kilogram mass is pulled upward with an acceleration of 3 meters per second squared. So I actually have a certain set of understanding here. So I have acceleration moving upward, and it's a positive 3 meters per second. It's going to be a positive value because I'm moving in the positive direction and I'm speeding up. So A is going to be positive moving up, which means that my upward force, my net force, has to be in the upward direction. My upward force has to be longer and more powerful than my downward force. Again, I draw the box. There is no surface because I'm pulling it in the air. I put my mass inside. I will always have my weight force vector going down, right, Fg. But in this case, my tension, whatever's pulling it upward, has to be larger than my Fg because my net motion is in this direction. My acceleration is a positive value. Here, I have an acceleration that's a negative value, right? So remember that your A positive or negative is really what you're going to be seeing. So here, my A is negative. I'm being pulled upward, but my acceleration is negative, which means that I'm slowing down. So what that means is, again, I have my box with the mass in it, no surface because I'm moving in the x and the y direction. But because I have a negative a, I'm going to be acknowledging the fact that my downward vector is going to be winning out, right? My acceleration, the direction of my acceleration, not direction of motion, direction of acceleration, is negative, so my negative pointing vector is going to win out. My tension vector will be smaller. Here's the next example. A 50 kilogram box, same kilogram box, descends but is slowed down by a rope. So remember that if I'm descending, I'm going backwards, but I'm slowing down, means that my v versus t graph is in the fourth quadrant and moving toward the x-axis, which means that I have a positive acceleration. So my upward force has to be larger than my downward force. It's not as clear on here, I apologize. My direction of motion is this way, but my acceleration vector is going to be positive. So here I'm showing that I'm slowing down my 50 kilogram box. My t is larger than my fg. And finally, I can have a 50 kilogram box. This is on a surface. So I have my surface line right here, my mass. And it slides along the floor and eventually slows to a stop. So really what's happening is that friction force is causing it to stop. Friction force always points in the negative direction. It always slows your direction of motion, and it gives me a negative acceleration. I'm slowing down in the positive direction, and so the only force vector that I have is this one. So sometimes you only have one force vector. Sometimes you have multiple force vectors, but you use the laws, the rules that we have for vector addition in order to figure that out. And remember that F net is also going to be the sign of your acceleration. If your F net is positive, your acceleration will be positive, and if your F net is negative, your acceleration will be negative.